in the next few lectures, 2 or 3 lectures, we will define the Fourier transform, look at its properties, and then prove what is known as the Fourier inversion formula and the Plancherel's theorem. So, that is the aim in the next few lectures. Okay. So, let us start. Fourier transform. So, we will define everything on Rn. Okay. So, sometimes it is easier to restrict to the real line, but we will do everything on Rn, but some computations will be done on the real line. So, let us start with the definition. So, take f in L1 of Rn. Okay. Its Fourier transform so this is denoted by f hat. Okay. So, that is defined by f hat of t equal to 1 by root 2 pi to the n integral over Rn f of x e to the minus I x dot t dx. Okay. So, that is the definition of the Fourier transform. Okay. So, I will not get into the history of this, there are several reasons why one uses the exponential. I will give an exercise which will give you one such reason for using the exponential. But let us look at the definition again. There is a factor of root 2 pi to the n here. So, some people do not put it here, they put a 2 pi here in the exponential. Okay. It does not really make any difference in the theory, but I will stick to this notation. So, I am taking a function in L1 and I am looking at the integral of f against e to the minus x dot t is the usual dot product on Rn, right, the usual inner product on Rn. So, it is a function defined on Rn, right. For each t in Rn, I have an integral which gives me some number, right. So, f hat is a function defined on Rn. Now, staring at it already tells you certain properties of the Fourier transform. You can take the modulus, for example, right, modulus of this would be less than or equal to, you can take the modulus inside, this has modulus 1, so that disappears and you have L1 norm of f, right. So, it immediately tells you that modulus of f hat of t is less than or equal to 1 by root 2 pi to the n integral over Rn mod fx dx, right, which is finite, right. So, and this part is independent of t, right. So, I can take supremum over t in Rn, right. So, this tells me that f hat is a function in L infinity of Rn. Okay. So, if I start with an L1 function and take the Fourier transform, I am going to land in L infinity. Okay. Well, it is slightly more than that, that is what we will prove next. So, you can think of this as a linear operator from L1 of Rn to L infinity of Rn for the time being, right. It is a linear operator. If I change f to f1 plus f2, it becomes the sum of the Fourier transforms, right. Alright. So, the first important result is what is known as the Riemann Labesgue lemma, which tells you a little bit more about the Fourier transform. So, you already know that it is a bounded function. If the function is in L1, then the Fourier transform is a bounded function. Okay, so that is what this. So, so various things follows from this, right, that it exists for all t, etc., etc. But you can say a little bit more. Okay, so if f is in L1, then f hat, the function which we have defined just now, is actually a continuous function which vanishes at infinity. So, it is a little bit more than being a L infinity function. Okay. So, L infinity is simply bounded, essentially bounded functions. This tells me that Fourier transform is actually uniformly continuous and it vanishes at infinity. Okay. So, let us prove this. So, you can use the property here that we have the L infinity norm of f hat bounded by the L1 norm of f, right. So, notice that from here we already have So let me write that down. Already have L infinity norm of f hat is less than or equal to that constant. So sometimes I may miss the constant 2 pi root 2 pi to the n. Okay, L1, right. So we have this for all functions in L1 of Rn, right. So as a linear operator, it's bounded from L1 to L infinity. Okay, the Fourier transform is a bounded linear operator from L1 to L infinity, that we already have. The additional property here is that it is continuous and vanishes at infinity, right. That is the Riemann-Labesgue lemma. So we want to say a little bit more about the Fourier transform. So let us see why it is continuous. Well, it follows immediately from the integral. So to prove that f hat is continuous, well, what will you do? This is the definition. To prove that this is continuous, you take a sequence Tn converging to T and you want to say f hat Tn converges to f hat T. Well, if Tn converges to T, e to the minus Ix dot Tn will converge to e to the minus Ix dot T. But they all have modulus 1 and it's bounded by mod f. So by dct the integrals will converge, right. So f hat is continuous follows from dct. Okay, straightforward from dct. Okay, so that's an easy part. In fact, uniform continuity also follows immediately from dct, but let's not worry about it. Since it vanishes at infinity, it will be uniformly. Any continuous function vanishing at infinity is uniformly continuous. Okay, so well, if you haven't seen that, that's a simple exercise. Okay, so let's prove that it is actually vanishing at infinity. For that, we use whatever we have already defined, like we defined those spaces Cc infinity of Rn and Schwartz space, right. So those are dense subspaces of L1 of Rn. So what we do is we take a dense subspace of L1 of Rn and prove that under Fourier transform it lands here, and because of boundedness property, all of L1 of Rn will go there, right. So that is basic function analysis. So we let's take function in let's say Cc infinity of Rn. Okay, so we saw that how to construct functions with compact support and smoothness, etc. in the previous lectures, right. So this is a rather rich class. It's dense in L1. So we use these functions and let's see how they decay at infinity. Okay. For that we need certain properties of the Fourier transform. So let's start with derivative of f. Okay, so df by dxj. F is a smooth function, right, C infinity function, so I can differentiate it. Well, it's compactly supported, so this is also a compactly supported function. Okay, so this belongs to Cc infinity. Okay, and so it will be in L1. So I can look at its Fourier transform, right. So if I look at df by dxj as a function in L1 and I look at the Fourier transform at the point t. Okay. This, well, let's write down the definition. So this is simply 1 by root 2 pi to the n integral over Rn df by dxj at the point x e to the minus I x dot t dx, right. That's how the Fourier transform is defined. Now I integrate by parts so that the derivative goes here. Okay, so integrate by parts. Integrate by parts. Of course, here the derivative is only in the jth variable. So you need to integrate by parts only in the jth integral. Okay, and remember that everything is compactly supported. So the endpoints, f at infinity and minus infinity will be 0. Okay, so there are no boundary terms. Okay, so when I integrate by parts, I am going to get the boundary terms vanish and there is a minus from somewhere, right. So it would be minus 1 by root 2 pi to the n integral over Rn f of x, and the derivative falls here, right. So d by dxj of this. What is d by dxj of this? Well, I will have minus I tj coming down, right. So it will be, and so that minus goes away. So I will have I tj e to the minus I x dot t dx, right. So it's a simple computation. The Tj has nothing to do with the integral, that comes out. What remains is f and e to the minus I x dot t is the Fourier transform of f. Right. So, this is simply I Tj times Fourier transform of t. Okay. So, that is just an easy consequence of integration by parts. Now, I can continue this, right. So, instead of doing it, let me do it once more. I want to say that Fourier transform decays rapidly at infinity, so that it goes to 0, right. So, this already tells me something. So, this is a certain property which you should keep in mind. When I differentiate the function and take the Fourier transform, on the Fourier transform side I am multiplying by the corresponding coordinate. Okay. So, derivative is transformed to a multiplication operator by under Fourier transform. This is something which you will see again and again, and it goes the other way also. If I multiply f with a coordinate function and take the Fourier transform, I will get the derivative on this side. Okay. So, derivative and multiplication are intertwined by the Fourier transform. That is the principle which you will see again and again. But for the proof of Riemann-Lebesgue lemma, let us continue that. I can look at the second derivative now. Right. Second derivative is also a CC infinity function, and I'll multiply f hat by once I Tj once more. Right. That is what will happen. Okay. So, similar computation will tell you, if I look at d square by dfx djx square and I take the Fourier transform at t. So, this is going to be I Tj square. So, that is minus Tj square times f hat t. Right. So, that is just repeating this procedure once more, right, because function is in CC infinity. So, we are not going out of CC infinity by differentiating it. Okay. So, now if you define so let delta be the Laplacian. So, this is summation d square by dxj square j equal to 1 to n. So, that is a differential operator, right. You look at derivatives, second derivatives in each coordinate and sum up, let us call that delta. So, this is called the Laplacian. So, you will see this operator again and again, Laplacian on Rn. Okay. So, I apply delta to f. So, this is simply a differential operator, right. So, if I apply delta to f, I will still be in CC infinity. I take the Fourier transform. For each of this I have minus Tj square, and when I sum up I will get minus mod t square, right. So, delta acting on f, this makes sense because this is a CC infinity function. Take the Fourier transform, because this is in L1 I can do that. This is, well, I will be summing up with respect to each of them, right. So, I will get minus Tj square summed from j equal to 1 to n, which is minus mod t square f at t, right. So, this is a simple formula which we get. Okay. So, let's use this to prove that it goes to 0 at infinity. Well, what does this say? This says that I have a CC infinity function which is in L1 whose Fourier transform is something like this. But the first thing we observed with Fourier transform is that if I take an L1 function, take the Fourier transform, I will get a bounded function. So, this is bounded, right. But this is bounded would mean f hat t is less than or equal to 1 by mod t square at infinity, but that goes to 0. Okay. So, let me complete it here. Since delta f belongs to CC infinity of Rn, which is contained in L1 of Rn, delta f hat, which is minus mod t square times f hat t, will be in L infinity, right. So, it is a bounded function. So, mod f hat t has a decay like 1 by mod t square at infinity, and so it goes to 0. So, this implies f hat belongs to C0 of Rn. Continuity we already know, now it vanishes at infinity, so it has to be C0. But this is a principle we will see again and again. If I differentiate, take the Fourier transform, I am going to get a multiplication on the other side. Similarly, if I multiplicate f by something and take the Fourier transform, I am going to get the derivative on the other side. Okay. So, multiplication operator and the derivative, these are intertwined by the Fourier transform. Okay. So, that is the Riemann-Lebesgue lemma. Now, there are several easy properties of the Fourier transform which you can observe simply from the definition. I will write down some of them, some properties, let us say. So there are several actions on Rn by various groups. Okay. Since they act on Rn, they will act on any function space on Rn, and so in particular on L1, and we want to see how the Fourier transform behaves with respect to those actions. So let us start with the simplest one. So this is a translation, right? Rn is an abelian group. You can translate elements in Rn. So similarly, you translate the functions, right? So you take a function, you take a point in Rn, and use that to so let us put an x naught, so that it's a fixed point in Rn. Use the x naught to translate the function. So look at tau x naught of f. Okay. At the point x to be f translated by the point x naught. This makes sense, right? So if f is in L1, then its translation is also in L1, right? Because Lebesgue measure is translation invariant. Okay. So if f belongs to L1, then tau sub x naught f also belongs to L1 of R. Okay. And I want to compute the Fourier transform of this and see how it is related to the Fourier transform of f, right. So this is already done here, right, in some sense. If I differentiate the function and take the Fourier transform, it is related to the Fourier transform of the original function by a multiplication. Okay. So we are trying to find something very similar. Okay. So let us compute the Fourier transform of f translated at the point t. Okay. Well, write down the definition. So these are very straightforward calculations, but let us do it at least once. E to the minus I x dot t dx, right. So this is the definition. Now I will use the advantage that I have a board, so that I do not need to write it again and again. This I can write as f of x plus x naught, right. That is the definition of the translation. Okay. But I want to sort of compute this. Best thing is to change the variable, right. So I want to change x plus x naught to something and then appropriate changes there. So this I can write as, well, I change x to x minus x naught, so I will get f of x here. Changing x to x minus x naught gives me e to the minus I x dot t times e to the x minus x naught, right. So I x naught dot t dx, right. Lebesgue measure is translation invariant, so there is no Jacobian, right. All that I am doing is changing x to x minus x naught. So this portion gives me the Fourier transform of f, right. This has nothing to do with the integral, it comes out. Okay. So this is nothing but e to the I x naught dot t f hat t, right. So translating the function and taking the Fourier transform gives me the product on the other side. Okay. So it's very similar to what we did with derivative, because that is at the infinitesimal level. So, well, something which you will learn later, the translations are sort of generated by the derivatives, and this is simply the exponential form of that. Okay. So right now that is enough. We will explain those things later if when we get to such things. So that is one simple property, and of course here I was saying that if you multiply the function and take the Fourier transform, you are going to get the derivative. Same thing happens here. Instead of translating the function, I multiply the function with an exponential, take the Fourier transform, I will get the translation on the other side. Okay. So just like derivative and the multiplication is intertwined by the Fourier transform, translation and multiplication by exponential is called modulation. They are intertwined by the Fourier transform. Okay. So let's do that as well. So this is one translation to, well, I will call it modulation. Don't worry too much about this name. So I take a point in Rn and multiply f with, so let us call that m sub x naught acting on f at the point x. So, I am defining an operator m, right. So, this is e to the I x naught dot x f x. So, all that I am doing is multiplying f by an exponential e to the I x naught dot x. Okay. And this is a function which has modulus 1, right. So, if f is in L1, the product is also going to be in L1, right, because modulus of this is 1. So, it does not do anything to f. Okay. So, this would be in L1 if f is in L1. Okay. So, I can look at the Fourier transform. Okay. So, let us compute that. So, mx naught f Fourier transform at t. Okay. This is much easier to compute. So, this is 1 by root 2 pi to the n integral over Rn. Mx naught f is the multiplication of these guys. So, I have f of x, I will write e to the I x naught dot x, that is mx naught f, and then I want to compute the Fourier transform e to the minus I x dot t dx. Right. So, this I can write as, because exponentials you can multiply, x is the one which is common. So, it is e to the t minus x naught, right. Okay. So, e to the minus I x dot t minus x naught, yeah. Okay. So, that is simply the Fourier transform at the point t minus x naught, right. So, this is f hat at the point t minus x naught. So, the translation multiplication by exponential became translation after taking the Fourier transform, right. Here it was the other way. So, Fourier transform intertwines translation and modulation. Okay. So, one has to be careful about the sign, okay, plus, minus, etc. But other than that, there is nothing too difficult to understand here, but it's an extremely important property, and that's precisely what is happening here. The derivative is like the translation that goes to the multiplication, and multiplication will go to the derivative. Okay. So, let's write down that as well. So, 3. Well, we have done one way, so let us do the other way. So, let f belong to L1 of Rn, and I want to multiply the function, right. So, let us take xj times f of x, okay. So, belongs to L1. So, I am multiplying f with xj is the jth coordinate vector. Then, then I want to say, then f hat is differentiable. Okay. So, I want to say multiplication goes to differentiation under Fourier transform. So, when I take the Fourier transform of xj times f, I want to say the answer would be the derivative of the Fourier transform, right. Here, when I took the derivative of the function, its Fourier transform was the multiplication of the original Fourier transform, right. Here we are going the other way. Then f hat is differentiable, and xj f hat at t would be some derivative, right. So, it would be d hat by tj at tj, and there will be plus or minus I or something, which we will put in after we compute the Fourier transform. So, you look at 1 by root 2 pi to the n integral over Rn xj f of x, right, e to the minus I x dot t dx, right. So, this is our Fourier transform, right. The function now is xjf, okay, not just f, xjf. Well, how will you compute this? So, what you do is you can club these two, okay. So, xj times e to the minus I x dot t, what is that? So, you differentiate the exponential with respect to the jth coordinate. So, let us start with f hat and prove that it is differentiable, okay, in the differentiable in the jth coordinate, okay, in the jth variable. So, wherever we have decay, so we have decay in the jth variable, right, xj times f is in L1 means that f has a certain decay in the jth direction, right, because xj blows up at infinity, right. So, even after multiplying by something which is blowing up at infinity, you are still in L1. So, that means it has certain decay in the jth variable. That gets reflected in the differentiability property in the jth variable for the Fourier transform. Okay. So, we are trying to prove that f hat is differentiable in the jth variable. So, you look at f hat of t plus, well, t plus h minus f hat of t divided by h, right, but only in the jth direction. So, let us write it as h times Ej, where Ej is the, right, that is a partial derivative, right. So, minus f hat t by h, right, where Ej is 1, sorry, 0, 0, etc., 1, 0, 0 and so on, right. This is the jth place, jth coordinate. Okay. So, you are looking at the partial derivative of f hat in the jth variable. Okay. But here there is nothing, right, this is just the difference of two Fourier transform divided by h. Well, what is that? That is easy to write down, 1 by root 2 pi to the n integral over Rn. So, Fourier transform of f at the point t plus h Ej. So, that is just f of x, right, minus the Fourier transform at t. Okay. So, in the definition of the Fourier transform, only in the exponentials all these things will come, right, t comes in the exponential, right. So, it is e to the I x dot this element minus x dot t divided by h, right. So, you will have e to the minus I x dot t plus h Ej, okay, minus e to the minus I x dot t divided by h. So, I have combined everything inside this, right. Okay. So, this is a straightforward computation. So, we nothing too difficult here, we are just using the definition, but we want to prove that f hat is differentiable. Well, for that you have to take the limit as h going to 0. Okay. So, we take the limit of this as h going to 0 and I want to put the limit inside. So, if you want to interchange integrals and limits, you have to use dct. So, use dct and I take the limit inside. This is simply the derivative of the exponential function in the jth variable. Okay. So, you will get xj times e to the minus I x dot. So, take limit as h goes to 0 and of course, use the fact that xj is in L1, okay, xjf is in L1, that is how you can take the limit inside, okay, because this will be bounded by xj times something and xjf is in L1. So, you apply dct, you can take the limit inside, okay, and use dct to get, this is simply the derivative of f hat with respect to the jth variable, okay. Here what will I get? So, this as h goes to 0 will go to the jth derivative of e to the minus x dot t, right, that is the function, right, at the. So, what is that? It would be e to the, so this would be minus I xj e to the minus I x dot t, right. So, remember x dot t is x1 t1 plus x2 t2 etc., etc., xn tn. Jth one will be simply xj tj. So, if I differentiate with respect to tj, I will get the xj down, right. So, that is all this. There is a minus sign, right. So, this is simply the Fourier transform of minus I xjf and you take the Fourier transform at t, right. So, that is all this is, right. Right, minus xj is the function which will come down and you have e to the minus I x t, right. So, that is just minus xj f and you take the Fourier transform at the point t. So, the derivative, so multiplication by xj goes to the differentiation of the Fourier transform, okay. So, you can put the minus I here if you want to complete the sentence, right. So, let us see minus I will come here, okay. So, minus I comes to here as 1 by minus I, that is simply I. So, that is the exact formula. So, this justifies what I was saying, that the Fourier transform intertwines multiplication and derivative and you can continue, okay, how many ever times you want to differentiate, you have to have that much decay. So, there is an intertwining of the smoothness properties and decay properties, right. So,
What is wrong with that argument that you are going to use?
I know you can. Okay. Yeah, it's possible to do it, but this would be more direct. That's all. Yeah. So the upshot of all this is that if I have decay on the function side, I have some smoothness on the Fourier transform side. If I have smoothness on the function side, remember that is the first computation we did, right? You differentiate the function. Then the Fourier transform has multiplication, but then Fourier transform is a bounded function, so there is decay in the Fourier transform side. So smoothness and decay are intertwined by the Fourier transform. So we saw dilation yesterday, so let us see how Fourier transform acts with respect to dilation. So let us take a delta positive and define f sub delta, okay, equal to f of delta x, right. F is some function in L1 of R. Okay, so you are simply multiplying x, the vector x by delta. Okay, so that is dilation. We can compute the Fourier transform of this. So, of course, if f is in L1, then multiplying by a delta in the variable does not change the L1 property. So, f delta at t is again 1 by root 2 pi to the n integral over Rn f delta x, right, f delta x times e to the minus I x dot t dx. What do? You change the variable so that you have f here and you can write it in terms of the Fourier transform of f, right. So, delta x you should change. So, what do? I can write. So, I will use the again take the advantage of the board. So, I can write this as delta x dot t by delta, right. So, delta gets cancelled. Well, I can put a delta x here, right, but then delta to the n comes out as the Jacobian. So, divide by delta, right. So, now put delta x equal to y, you will get fy e to the minus I y dot t by delta to the n, but that is a Fourier transform at t by delta, right. So, this is simply 1 by delta to the n f hat by t by delta. So, the dilation goes to dilation in a different manner. Okay, so, that is something which you should. Some more properties. So, multiplication by delta is a linear map, okay, and this is simply the determinant of that linear map delta to the n. Okay. So, instead of multiplying it by a delta, you can actually look at a invertible transformation and do the same calculation. So, well, exercise if you like. So, let us say A from Rn to Rn invertible linear map, okay. Then look at f sub a at x, define it to be f of ax, right. Just like multiplication by delta, here I have a very general linear map, right. What would be the Fourier transform? Compute the Fourier transform of f sub a. Okay, for any linear map. Okay, so that's one. To conclude that if A is a orthogonal matrix, well, let us say so n, so orthogonal matrix, okay, and determinant 1, then well f sub a at t would be A or A transpose. Yeah, I think A. Yeah, fine. Anyway, that's Fourier transform commutes with rotations. Okay, that is all this says. We will use these things when it is necessary, but this is easy to compute. You do exactly the same computation, right? So, you will have Ax here e to the minus I x dot t. So, change that x to Ax, but then you should put appropriate thing here, right, to or A goes to the other side as A transpose inverse and things like that. So you put that there, and then there is a Jacobian. So you will get a 1 by determinant to the determinant A to the n f hat at A inverse T or A transpose inverse T or something like that here. Okay, so it can be easily computed, but most of the time one uses the dilation and the result for the orthogonal matrices. Okay, so let us most important property we left out that that's what happens with the convolution, right? So convolution. So take f and g in L1 and we'll redefine the convolution a little bit. Okay, so f convolve with g x. Well, if you remember, we defined it to be f of x minus y g by dy. Right, this is what we defined, but I'll put an extra 1 by root 2 pi to the n here. Okay, so that's because my definition of Fourier transform has that factor in the beginning. Okay, if you had the 2 pi with the exponential, this is not necessary. Okay, so then, well, if I take two functions in L1, I know that the convolution is also in L1, right? L1 convolve with L1 lands you in L1. Okay, so I can take the Fourier transform. So f star g at t, well, so 1 by root 2 pi to the n integral over Rn f star g at x e to the minus I x dot t dx. This is the definition of the Fourier transform equal to, well, so here I have an integral, right? So I plug in that integral, so there is another 1 by root 2 pi to the n. So I have 1 by root 2 pi to the n integral over Rn 1 by root 2 pi to the n integral over Rn f of x minus y g y dy, that is f star g, and then there is the exponential, right? So e to the minus I x dot t dt dx. Okay. Well, so let us compute that. So this is the integral form of the translation going to multiplication by exponential. Okay, so sort of the derivative one was the infinitesimal version in the sense of taking limits and so on. This is sort of in the other direction, but they are all same essentially. Well, let's so e to the minus I x dot t, right? So if I want to integrate with respect to x, so let's write this as e to the minus I x. I have an x minus y here, so I put an x minus y dot t, okay, and cancel whatever I have added. So I have only e to the minus I x dot t. So I have e to the minus I x dot t, but there is an I y dot t extra, right? So I cancel it by e to the minus I y dot t, right? Now I integrate f of x minus y e to the minus I x minus y dot t dx. Lebesgue measure is translation invariant, so y disappears. So I will have f of x e to the minus I x dot t dx, that is f hat. What remains is e to the minus I y dot t g y dy, that is g hat. Okay, so this is simply f hat t g hat. So convolution goes to multiplication. Okay, this is an extremely important property of the Fourier transform. Okay, so what we have seen is several properties of the Fourier transform, right, starting from translation, differentiation, convolution and so on. Let us compute the example, let us compute the Fourier transform of some function, some easy or elementary functions. Okay, so first example is, so we'll look at n equal to 1 where the computations are a little bit easier. So we are looking at L1 of R, okay, the real line, okay, dimension 1. So let us take the function indicator of let us say minus 1 1. Okay, so this is of course a function in L1 of R, right, and I want to compute the Fourier transform of chi minus 1 1. Well, let us do that. So chi minus 1 1 Fourier transform at the point t. Okay. By definition, this is 1 by root 2 pi. Well, there is no n, right. So, it is just 1 by root 2 pi integral over r, well, integral over r chi minus 1 1. So, that would be just minus 1 to 1, right, and 1 times the exponential. So, that is e to the minus I x dot t dx. Well, there is no x dot t because we are in the real line. So, it is just x t, right, e to the minus I x t. Since it is exponential, you can integrate it explicitly, right. So, it is e to the minus I x t divided by minus I t, right, and then evaluate it at minus 1 and 1. So, you will get exponential minus exponential. Okay. So, you will get the sine function. So, this you can calculate to be sine t by t. Okay. Well, the one thing to note here is that sine t by t is not in L1 of R. Okay. So, if you like exercise, prove that sine t by t is not in L1 of R. So, if I take an L1 function and take the Fourier transform, I need not get something in L1. Okay. I go to C0, of course, this is a continuous function which will vanish at 0, at infinity, but I may not be able to say anything more than that. So, this you can see as an exercise because of the 1 by t. Okay. So, think about intervals around n or n pi or something like that, where this is 1 and you will get something like summation 1 by n from that interval. Okay. So, prove that the integral vanishes, is infinity. Well, but the improper integral will exist. So, that is, as of now, that is not important. I will give it as an exercise later. Okay. So, this is one example. Second example is very important again, n equal to 1. So, let us consider the function phi 0 of x to be equal to e to the minus x square by 2. Okay. So, this is a Gaussian, right, exponential. One of the most important functions you will see in Fourier analysis is this exponential. So, I called it phi 0 because you will see later why there are phi 1, phi 2, phi 3 and so on. Well, let us try to compute the Fourier transform of this. Okay. So, I want to compute phi 0 at t. Of course, this is an L1 function, right, it is an exponentially decreasing function. It is a Schwarzschild function actually. Right, you can multiply this with any polynomial, differentiate, you will still get a polynomial times exponential which is bounded. Okay. So, the Fourier transform of phi 0 is 1 by root 2 pi integral over r e to the minus x square by 2 e to the minus I x t dx. Okay. So, I do not know if you have seen this before in complex analysis, but you can compute this integral. Let us try to do that. Well, there is an x square, there is an x term, so you complete the square. Okay. So, you can write this as 1 by root 2 pi integral over r. Okay. So, let us take minus half outside. Okay. So, I have x square plus 2I x t. Okay. Now, I want to complete the square. So, I have x square and I have 2, then there is an it extra here, right. So, that is the second term. So, I should be to complete the square, I should be adding it square, correct. So, this would be a square plus 2ab plus b square, right. So, I have a plus b square, but then this is an extra term I have added. So, I have to cancel that. So, I have to add half it square, right. So, plus half it square. Okay. So, I have not done anything except completing the square and adjusting. Okay. And then I have exponential. So, this will give me e to the minus half x plus it whole square, correct. That is the first term. Then I have this term. What is this term? This is minus t square and there is a half. So, and that comes out, right. So, dx times e to the minus t square by 2. Okay. So, I am computing this by hand. So, here I completed the square, I have this term, this is the extra term which I added and cancel. but I square gives me a minus and there is t square by 2, right. So, exponential of minus t square by 2 has nothing to do with the integral, that comes out. So, now I need to compute this. Well, how will I compute this? So, think of this as x plus I t as z, and I am looking at e to the minus z square on the real line. So, instead of looking at so this is what you do with usual contour integration. So, I have, let us say this is t, and we are looking at, so for a fixed t we are looking at e to the minus half z square, right, t is the imaginary part. So, I am integrating over this line, okay. So, I can shift that to integral over this line by, well, what do? I cut it at let us say capital R, okay, and this would be t plus IR, R plus IT, and this is R minus R plus IT, and you look at this closed curve, right, and the function you are looking at is e to the minus half z square, right. So, that is an holomorphic function, right, that is an analytic function, entire function. So, if I integrate over this, I will get 0. So, the integral over minus r to r is same as negative of this integral plus this integral, negative of that integral plus negative of this integral. Then you prove that these two pieces will go to 0 as r goes to infinity, and so the integral over this line and integral over this line will be same. Okay. Have you seen this before? Yeah. Okay. Well, if not, it is a good exercise. Okay. So, you can let me repeat the argument. So, here looking at this, we call this the variable z. So, that is e to the minus half z square. This is an entire function. By Cauchy's theorem, whatever closed interval, closed curve I take, the integral will be 0. So, but I am trying to compute the integral over this line, right, and I want to say that is same as the integral over this line. So, you cut it at some point r to minus r and look at this closed curve, integral of this function over this closed curve is 0. So, integral over minus r to r would be negative of these three integrals, right. You prove that, see, this is a fixed length, right, it is only from 0 to t is fixed, okay. So, that is a compact interval and I have exponential decay. So, you will see that this goes to 0 as r goes to infinity, similarly this goes to 0 as r goes to infinity. So, the integral over the real line will be same as the integral over the line at t, which means that this is independent of t, right, I can shift it to any line I want. So, you can put t equal to 0. So, you will get e to the minus half x square dx 1 by root 2 pi is 1, right, that is the normal distribution, right. So, total measure is 1. So, you prove that 1 by root 2 pi integral over r e to the minus half x plus it square dx is same as 1 by root 2 pi integral over r e to the minus half x square dx, okay, which is 1. This is true for every t. Okay, so this integral does not depend on t. Okay, so that is one way of doing it. But the consequence of the computation is that if I take phi 0 of x to be the Gaussian e to the minus x square by 2, then the Fourier transform is e to the minus t square by 2, which is itself, right. So, this is phi 0 of t. So, Fourier transform of phi 0 is phi 0. Okay. So, it is an eigenfunction for the Fourier transform with eigenvalue 1. So, let me stop with an exercise. You can do this in a slightly different way. Exercise, okay. Prove that phi 0 prime plus x times phi 0 is 0, phi 0 hat prime plus x times phi 0 hat equals 0. This implies phi 0 hat equal to some constant times phi 0. Compute the constant. See, by evaluating at t equals 0. Okay. So, these are just first order differential equation. So, prove that phi 0 and phi 0 hat satisfies the same first order differential equations with smooth coefficients. So, they will have to be same, right, except for a multiplying factor, right, because the solution has one dimensional space as the solution, because it is the first order differential equation, and you can compute the constant by evaluating it at 0 or something like that. So, here this is trivial because it is e to the minus x square by 2, you differentiate it, you will see that it is 0. Here you are differentiating inside the integral sign, so you have to use dct to justify it, but this also will follow. Once you have these two, they will have to be multiples of each other because these are first order differential equations, and from that you will get this, and then you can compute the constant by evaluating it at some point, okay, t equal to 0. Alright, so we will continue with Fourier transform in the next lecture.